One of the most important characteristics of an algorithm is its runtime, how long it takes to do its work. Different algorithms have different runtimes that can vary differently with different data sizes. You've probably heard about algorithms being order n or n squared. In fact, in 1020, we already talked about an n cubed algorithm, but now it's time to get a little bit more rigorous about algorithmic analysis. We will mostly describe an algorithm's runtime in terms of functions of its input size, how much data it's working on. This input size will typically be expressed in terms of the variable n, which represents the number of pieces of data that we're working with. That could be a number of floating point numbers, or a number of objects, a number of students, a number of records that we're processing. The functions of n that we'll see will typically be things like logarithms, linear relationships, quadratic functions, cubic functions, or exponential functions. We'll talk about upper bounds using a notation called big O, lower bounds using a notation called big omega, and exact bounds using a notation called big theta. Let's start with big O. The big O notation means that we can find positive constants that satisfy this inequality. For whatever f of n is, we can find a value of n beyond which our algorithm's runtime is always less than f of n. For example, if f of n is n squared, this means we can find a value of n beyond which the running time of our algorithm is always less than n squared times whatever the positive constant c is. It doesn't matter what the values of c and n naught are. If we can find them, then we can say that this inequality has been satisfied. Let's look at a simple example. In this plot, the dashed black line at the bottom is a linear relationship. It represents a value that grows twice as much for every doubling of input size, for example. Now it would seem that the blue line represents a runtime which grows superlinearly, faster than linearly. This looks kind of the same if we look at a bigger picture, where we extend to looking at more data. If we look at an even bigger picture, this still seems to be true, but we see that there's an interesting trend here. Although the blue line is not strictly speaking linear, it's getting closer and closer to linear as we work with larger and larger data sets. If we look at this next picture, we can see that by adjusting the slope of our linear line slightly, we can find a crossover point. Below that crossover point, the blue line is above our strict linear line, but above the crossover point, our blue line is below the strict linear line. We can exaggerate this effect by choosing a larger slope or a larger value of c in the inequality that we saw earlier. It doesn't really matter what the value of c is, and it doesn't really matter what the value of n naught is where the crossover point occurs. The point is that because we can find these constants, this means that the algorithm's runtime is big O n. That is, it's on the order of a linear algorithm. Ignoring constant factors, we can expect that doubling the size of our input data would cause the algorithm to take about twice as long to run. When we increase the size of the input data by a factor of 10 or 100, we would expect the runtime to increase by a similar factor. Again, there may be a constant factor, so increasing by 10 may actually cause it to increase by 20. Increasing the input size by 100 may cause the runtime to increase by 200, but the constant factor is not very important. What's important is that we are increasing approximately linearly with the size of the input, not quadratically, or cubically, or exponentially. So that's the big O notation. It provides us with an upper bound on the runtime of an algorithm. In addition to big O notation, we also have big omega notation, which provides a lower bound on execution time, using exactly the same kind of approach. And we also have big theta notation, which is an exact bound. If an algorithm is big O f of n as well as big omega f of n, then we can say that it is big theta f of n. For example, if an algorithm is cubic in the upper bound and cubic in the lower bound, then it is exactly cubic. We can analyze the worst case behavior of an algorithm by simply counting the operations that it performs. A for loop that iterates through n elements will perform n times the number of operations that are inside of the for loop. When we have loops inside of loops, we analyze them from the inside out. We can see an example of this when we go to class when we'll look at the analysis of the matrix multiplication algorithm. When we have statements that follow each other, we can simply add together the number of operations each performs. Conditional logic, such as an if-else, results in the worst case of either following the if block or the else block. We have to evaluate the condition and then perform one or the other. Things can get a little bit more complicated when we do a function call, but we need to simply analyze what the function call's performance is first, and then go back to where we were in the broader algorithm.